60 degrees of incline marks the limit where a massive transportation system hangs suspended in midair. In the freezing Swiss Alps, mountain cliffs rise almost straight up. Why attempt to build here? It seems impossible to anchor heavy machinery on such a face. However, the system is held in place by only a few steel cables stretched across kilometers of open space. One can notice how the cabin is pulled almost vertically up the stone wall. At first glance, the ascent looks smooth, but in reality, the most astonishing part lies behind the scenes. This is the steepest cable car ever built in the world. But this is just the beginning of the complexity. Workers must suspend themselves thousands of meters above the ground. They install each pulley and tighten every bolt manually. It is visible how they run each steel cable through the guides. On this extreme construction site, even the smallest mistake leaves no second chance. Thus, the structure secures its position on the cliff. 159% is the maximum gradient conquered by the Steckelberg-Mühren cable car line in southern Switzerland. This region remains one of the most rugged mountain areas in Europe. Why do engineers design for such extreme angles? At first glance, the slope appears too steep for any heavy cabin. But this capability allows the system to traverse terrain where other transport methods cannot operate. The mechanism climbs nearly 800 meters in elevation. One can notice how two cabins, each holding up to 85 passengers, move steadily along the cables. The line stretches over 1.1 kilometers, pushing engineering beyond traditional limits. But this is just the beginning. Very few transportation systems anywhere in the world attempt such a vertical challenge. It is visible how the equipment endures fierce winds and heavy snow in this harsh environment. Engineers install and operate the suspended system, knowing that even the smallest mistake is not an option. The cabin reaches the station, completing the journey without haste. 60 degrees of incline is the extreme angle engineers ultimately selected for the cable car route. The construction of such a complex system begins not on the mountain, but with the calculation of every factor on paper by seasoned specialists. Ordinary engineering solutions do not apply here, as the project requires accounting for the height of each tower, the tension of the cables, the load of the cabins, and even the vibrational resonance caused by wind. A single millimeter of error in the drawings could render the entire system unsafe for future passengers. This bold design decision was the only way to conquer the specific terrain at the destination. But this is just the beginning. Immediately after the blueprints are finalized, the focus shifts to the construction site, located thousands of meters above sea level. Why do engineers resort to using explosives on an already unstable cliff face? It would seem safer to dig manually or use mechanical excavators. But in reality, the bedrock is too hard for standard digging, and natural flat ground is non-existent, making controlled blasting the only way to carve out a foundation without shattering the mountain. Engineers drill grid patterns of holes spaced from a few dozen centimeters to over 1 meter apart. Each borehole receives a precisely calculated charge of explosive energy. The charges detonate in a strictly timed sequence rather than all at once, splitting the rock in the intended direction. One can notice how the dust slowly settles, revealing the newly formed flat surface. This method prevents dangerous cracking in the surrounding rock mass, preserving the mountain's structural integrity. Afterward, heavy machinery clears the broken debris, leveling the surface until the load-bearing capacity meets strict standards. Only when the foundation reaches the correct elevation and stability does the process move forward. Building a station at this altitude presents a logistical paradox. There are no roads for trucks or cranes to deliver materials. To solve this, builders install a temporary cable car line that acts as an aerial logistics system. It operates on principles similar to the main system, but focuses purely on cargo. Each trip carries between 1 and 3 tons of supplies, ranging from steel beams and cement bags to formwork secured on suspended pallets. The transport process is slow and methodical, with distances stretching hundreds of meters over sheer cliffs. A single delivery trip takes 20 to 40 minutes. Every lift is calculated against the current wind conditions, as strong gusts can cause the suspended load to swing dangerously near the rock face. Once the materials arrive, the team sets out the building's center line and drills deep into the bedrock to install steel anchor rods. Foundations are poured using concrete that requires strict thermal control. Because of the cold mountain conditions, the mixture must be compacted and cured at specific temperatures to achieve the necessary strength. After the concrete sets, the formwork is removed and the structural frame of beams and load-bearing walls rises from the stone. On top of this skeleton, workers install large steel bases and support frames to accommodate the future sheaves and mechanical equipment. It gets more complex further on. The station is then enclosed in a protective outer shell of metal panels and glass. This cladding is not merely aesthetic. It shields the sensitive internal machinery from heavy snow, ice, and high-altitude winds. While the station takes shape, the heart of the system is being prepared in a specialized steel cable manufacturing plant. High-strength steel is drawn into thin wires with precise diameters. Giant spools wind these wires, which are then twisted together in a predefined pattern to form strands capable of withstanding enormous tensile forces. During this twisting process, sensors continuously monitor the tension of each individual wire to guarantee even load distribution. The cable then passes through pressing and compacting systems that stabilize its internal geometric structure. At first glance, the cable looks like a simple steel rope, but in reality, it is a complex composite often coated with lubricants to resist corrosion. Each massive reel undergoes strict testing for elongation and dimensional accuracy before leaving the factory. Transportation becomes the next challenge, as each reel weighs several tens of tons. Heavy-duty cranes load them onto specialized low-bed trailers, which must navigate narrow mountain roads with sharp turns. Although the physical distance might be short, the complexity of the route means the delivery process can take up to a week. Simultaneously, the towers are being fabricated in a separate facility. Instead of monolithic structures, the towers are produced as individual steel modules, machined and pre-drilled with high precision. This modularity is essential because the installation sites are inaccessible to ground vehicles. Each section is suspended beneath a helicopter and flown directly to its point on the mountainside. One can notice how the helicopter pilot hovers with extreme steadiness while workers guide the suspended module into place. The tower is assembled from the ground up, with every section secured by hundreds of high-strength bolts tightened to precise torque values. Before the next module is added, the vertical alignment is checked with surveying equipment, as even a tiny misalignment at the base would be amplified catastrophically at the top. Once the structure is topped out, the cable guide roller assemblies, weighing hundreds of kilograms, are lifted and installed. Everything is now ready for the most critical phase, cable pulling. It works like a progressive chain. Engineers start by pulling a light temporary rope through the towers using a helicopter or pilot line. This small rope pulls a heavier one, and that rope pulls an even heavier one, until the system is strong enough to drag the massive main cable up the mountain. High-capacity winches control the uphill force, while braking systems at the bottom prevent the cable from sliding back or sagging into the rock. The cable moves at a slow, monitored speed, suspended in the air to avoid abrasion against the ground. Once the main cable runs the full length of the line, the ends must be joined to form a continuous loop. This leads to the splicing stage, which requires exceptional human skill. Workers stand on suspended platforms high above the ground, protected only by safety nets. It seems obviously simple to join two rope ends, but in reality, splicing steel cable is a manual art form that tolerates no errors. The two ends are untwisted, and the individual bundles of wire are interwoven by hand according to a complex sequence. When the cable is placed under tension, these interwoven strands tighten against each other, creating a seamless bond with no mechanical weak points. The loop is now complete. The process transitions to the installation of the cabins. Manufactured in a factory, each cabin is custom designed for the specific route, using aluminum alloys to minimize weight while maximizing strength. Exterior panels, safety glass, and automatic door systems are assembled directly onto the frame. Before shipping, the suspension system and damping components are rigorously tested to ensure they can handle the vibrations of the line. Transporting the cabins to the site often requires another round of helicopter lifts. Technicians attach each cabin to the cable, aligning the suspension system to prevent twisting and ensure proper balance. Following the mechanical install, electrical engineers route power cables and communication lines through the station. Control cabinets are wired to integrate the main drive, backup power, and emergency sensors. The heart of the operation is the drive unit. High-power electric motors transmit torque through a gearbox to the large drive sheaves that move the cable. This system must provide smooth acceleration and precise speed control under heavy loads. Finally, the system enters the testing phase. The line runs for hours without passengers. Engineers simulate different load conditions using empty cabins and test weights. They monitor vibrations, braking response, and wind behavior to ensure every parameter falls within the design limits. Only after these exhaustive tests confirm absolute stability is the cable car line officially opened for service. Thousands of components merge into a single unified system. The construction path stretches from the initial design drawings to the moment the system is ready to operate. This represents an extremely complex process of industrial assembly. But this is just the beginning. Why focus only on the main stages of such a massive project? The depth of the technology makes it impossible to cover every single mechanical detail. Yet the safety of the line depends on the accuracy of each element. Precision is maintained at every level. One can notice how the cabins stabilize as the main drive engages. At first glance, the finished line looks simple, but in reality, it is the result of rigorous calculation. Technical insights ensure the mechanism remains accurate during future use. The cycle is established. The cable car line enters its operational phase.